Kia ora and welcome to this video on question 5 of the 2018 Skull Calc exam. Two parts to this question. The first part, complex numbers problem, which is quite algebraic, and question 5b, a neat sequences and series problem about spherical ball bearings, which are stacked up kind of like ice cream scoops in a cone. Alrighty, first part, question 5a. Given that z equals x plus iy and z to the power of -1 is equal to a plus ib to the power of -1 plus a plus ic to the -1, where a, b and c are real and a, b and c don't equal 0. Find in terms of a, b and c an expression for the real part of z. Okay, so start off with the equation that we're trying to work with. Z to the -1 equals a plus ib to the -1 plus a plus ic to the -1. Okay, we can't just go all good. These are all reciprocals. So let's just flip them all upside down. Doesn't work. Okay, like a half plus a half is equal to a whole, but 2 plus 2 doesn't equal the reciprocal of 1, right? We can't just reciprocate things like that. But what we can do, though, is put these fractions together. Because the question is asking us to find the real part of z, and at the moment we've got an expression for the reciprocal of z. So let's put those right-hand side fractions together. A plus ic plus a plus ib all over a plus ib times a plus ic. That's 1 over z. Okay, now we have a fraction equals a fraction, so we can actually flip these upside down. Like if we have a half equals a half, then of course the reciprocal of the left is the same as the reciprocal of the right. So z is therefore equal to a plus ib times a plus ic all over 2a plus I times c plus b. I'm just putting the numerator together. I've got the real parts, the 2a's, and the imaginary part is c and b, both with i's. Now, of course, if we want to find the real part of this, we need to put it into a standard format. At the moment, it's a complex number divided by a complex number. So we multiply by the conjugate of the denominator. I also need to expand the brackets in the numerator. So I've got a times a, and I've also got ib times ic, which is I squared bc, negative bc. That's me going a times a and that times that first, because they're the real parts. And then I'll do the imaginary part second, which is iba and aci. iba and AC with an I. And that's actually, I'll colour coordinate that for you guys. Is now I've lost track of what I did. They came out of the purple ones. The denominator is equal to 2a plus ic plus b times 2a minus I times c plus b. That comes out to be 4a squared plus c plus b all squared. Okay, if you take a complex number and you times by its conjugate, you get the real part squared and you get the imaginary part squared. And then the other thing in the numerator is 2a minus I times c plus b. Now, I've left it like this because we only want the real part of z. To get the real part, we want the real stuff in the numerator only. So the real part of z is going to come from taking the real bit here and timesing by the real bit there, or taking the imaginary part here and timesing by the imaginary part there. Okay, those are the two things that give real stuff. So it's going to be a squared minus bc times 2a, or it's going to be BA plus AC times C plus B, and there's an I squared in there which is -1, which goes with the other minus to make a plus, all divided by the denominator. Okay, so that there is the real part of Z in terms of A, B and C, and we can tidy it up a little bit. Okay, so if I expanded out some stuff, I've got 2a cubed minus 2abc plus bac plus ac squared plus b squared a plus acb. Those cancel. All over 4a squared plus c squared plus 2bc plus c squared. Expanding that didn't really achieve anything because they don't simplify. So we've got 2a cubed plus ac squared plus b squared a all over 4a squared plus c squared plus 2bc plus c squared. And that's the answer. Okay, the second question is spherical ball bearing. Okay, so we've got a 2D representation of this. We're told that they're spherical. The first thing is the spherical thing, the volume of it is 4/3 pi r cubed. And these ball bearings are all different sizes. The first one which sits, if you think about this as an ice cream cone, should have made it orange, but my bad. The first ball bearing that sits in the top of it is like the first scoop. The second ball bearing underneath is the second scoop, and so on, and these scoops get smaller and smaller and smaller. Okay, so that's what we need to think about it. They're actually spheres sitting in there. We're told that the spherical ball bearing, a radius 20 millimeters, just fits inside a metal cone touching at A and B. The centre C of the ball bearing is 120 millimeters from the vertex of the cone, so that's all given in the diagram. Beneath the top ball bearing is another spherical ball bearing, and beneath that another, and so on, as shown in the diagram. After the first ball bearing, each ball bearing touches the one above it and just touches the sides of the cone. So they're stacked in, squashed in. Okay. Find the radius R2 of the second ball bearing. Alrighty, so if we set up this diagram here, we know that this is 20. We know that that's 20. Actually, missed the centre's not in the right place. But if I draw a line out up there, that's 20, which makes this length here 100. And we're finding the radius of the second ball bearing, so R1 is 20. If I draw a centre there, draw another line out there. The reason I'm drawing lines from the centre out to the side is because they're tangents, which means we're actually making similar triangles here. And this one here is R2. This length here is R2. And this length here is R2. Okay, so we've got a small triangle, which I'll colour in yellow. This triangle here is similar to the bigger triangle that we already had, which I could colour in blue there if it lets me. But you get the point there, right? That triangle there in blue, Mag's pride with the colours, is similar to the yellow triangle. They have the same slopes, the same angles, and so on. So what we have is that 120 over 20, so the total height of the blue triangle, sorry, it's not the height, it's the hypotenuse. The hypotenuse of the blue triangle, 120, divided by the small radius 20, is equal to the hypotenuse of the yellow triangle, which is 100 take away R2, And if I just, this length here is 100 minus R2. And that is divided by the R2 using the similar triangle relationship. And we can solve that because the left hand side is 6. 120 divided by 20, I can move the R2 up to the left hand side. 100 minus R2, and then I can put the minus R2 on the other side and divide by 7. I've got R2 equals 100 over 7. Just going to take that with me down to do some working. So that's the first answer. And question then asks us to find an expression in terms of n for the radius of the nth ball bearing. So this question is scaffolding us into the third part. So I'll just repeat this process. This time, just to have a look at one more. Whenever there's a sequence or series, try and explore it by seeing if you can find a pattern between the first few terms. So if I put that line back in there, and that was 20, and that was 20, oopsies, not 200, and then I had R2, another R2, R3, another R3, and then this is R3. Using the this triangle here in yellow this time, got R3 over the hypotenuse of that triangle, which is 100 minus 2R2, because 100 goes up to here, minus 2R2 minus 1R3, and that is also equal to 6, 120 over 20. Okay, so I'll take that one. The cool thing is I already know what R2 is, so I can just sub in R2 and solve for R3. But R2 is equal to 100 over 7. So I've got, if I solve that, 6 equals R3, 100 minus 2 lots of R2, 100 minus 2 lots of 100 over 7. Okay, and then take that up to the left hand side. Move the minus 6R3 to the other side, so it's 7R3, and divide by 7. We've got R3 is 500 over 49. And look, you can do that one more time, but I won't personally. But if we look at R2 and we look at R3, if we do it one more time, you'll pretty much confirm what you think it is. So we've got a sequence here. R1 is 20. R2 is 100 over 7. R3 is 500 over 49. If we look at that, it's timesing by 5 and dividing by 7. So timesing by 5/7. So R4 would be 2500 divided by 7 cubed. And the question asked us to find a expression in terms of n for the radius of the nth ball bearing. So therefore Rn is equal to 20 times by 5/7 to the n minus 1. Okay, and that checks out because if we make n equal 1, we got 20 times 5/7 to the 0, so 20. If we make n equals 2, the power becomes 1 and we get 20 times 5/7. Okay, and then the last question suppose the sequence continues on infinitely. Show that the maximum volume of all of the ball bearings is equal to that. So that means the total volume. Okay, obviously the maximum volume of an individual ball bearing is just the top one, which we could go 4/3 times pi times 20 cubed. But this is talking about the total volume of all of the ball bearings. So we need to add up these numbers. So we've got volume total is equal to the first one, 4/3 pi times 20 cubed, plus the second one, 4/3 pi times 100 over 7 cubed, plus the third one, 4/3 pi times 500 over 49 cubed, plus, and it goes on forever. The maximum volume of the total is saying that it's limiting to some value, because we keep on adding ball bearings, but the ball bearings are getting smaller and smaller, so it is possible that there is a limit to the volume in total. Okay, so we need to add up this thing. We've got a common factor of 4 pi over 3 in all of them, and then we've got to multiply this by the radius cubed, 20 cubed plus 100 over 7 all cubed plus 500 over 49 all cubed, going on to infinity. And the reason why the second part of the question was in there was to sort of assist us with the fact that there is a common factor of 20 in all of these expressions. Okay, 100 over 7 is the same as 20 times 5/7, and this one here is 20 times 5/7 squared. So we've got 4 pi over 3 times 20 cubed times 1 plus 5/7 cubed plus 5/7 to the 6, and so on. Just think about where that came from. We've got 20 cubed times 1 is 20 cubed. 20 cubed times 5/7 cubed is 20 times 5/7 all cubed. 20 cubed times 5/7 to the 6 is, have I done that one right? Five sevenths to the 6 is 5/7 squared cubed. We've got 5/7 squared times 20 all cubed. Yep, that's good. And so on. So the 20 cubed can pull out the front of the sum. And what we need to add up is 1 plus 5 over 7 cubed plus 5 over 7 to the 6, etc. Now this is called a geometric series, and you might have learnt about this in level 2 if your school did sequences in series. To add up a geometric series, or first up, why is it a geometric series? It has a first term, a equals 1, usually a is given to this, and then it has a ratio of 5/7 cubed. So the terms that we're adding up in series, a series is a fancy mathematical word for a sum. The terms are getting bigger by a ratio, and in fact in these terms they're getting smaller, because 5/7 cubed, if I just work that one out, is 0.36, and 5/7 to the 6 is 0.13. So the terms are getting smaller, which is helpful. If they were getting bigger, then the ball bearings would be getting bigger and we wouldn't be able to find the total volume. But a geometric series is a sequence, a sum of a sequence, where the terms are in some ratio. And the sum, an infinite sum, is a over 1 minus r. There's heaps of proofs for this on the internet that you can look up. In the question itself, we were given we were given this formula here, you had to realise that this one here and this one here were irrelevant. They're arithmetic sequences in series, and then this one here is the geometric sequence, and the SN is the geometric series. They're level 2 formulas, but what we're doing is making n go to infinity. So, and r is less than 1, the ratio, because the radiuses are getting smaller. So the radius to the n, if n isn't going to infinity, this term here disappears and this term here disappears. Oh no, it doesn't. R to the n does. So we get t1 over 1 minus r, and I just call t1 equal to a. The first term is usually called a. So that's where that formula came from, but I've seen it before, so I've memorized it. Not so good if you haven't done sequences in series before. 4 pi over 3 times 20 cubed times by a first term of 1 over 1 minus the ratio, which is 5/7 cubed. And it asks us to get it into a format which is 5.488 times 10 to the 6 times pi over 327. I think the reason why they've done this is just so that you can't fudge the answer. They've put it in a funky format for that very reason. So we're looking for 5.488 times 10 to the 6 pi over 327. Okay, let's see what this bracket comes out to be. 1 divided by 1 minus 5/7 to the power of 3. Okay, that equals 4 pi over 3 times 20 cubed times 343 over 218. Okay, and the whole thing in the front, so 343 over 218, if we times it by 20 cubed, times by 4 pi, no, sorry, just times by 4 and divide by 3, we get 16782.87462 pi. Okay, let me just check. 5.488 times 10 to the 6 divided by 327 is exactly the same thing, which equals, I'm just going to drag that down there. They've done something really random with the, where have they got the 327 for a start? Maybe if you leave it as a fraction. 4 times 343 divided by 3 times 218 times 20 cubed. And my calculator doesn't give it to me as a fraction. Oh well, it is equal. I checked. So not a terrible question, except for the fact that that geometric series comes back to bite you if you've never seen it. Then it doesn't come back to bite you, it just bites you. Alrighty, catch you in the next video.